Welcome back. This is the second video in the series on dimension reduction. I'm going to move into discussing with you the common dimension reduction techniques. There are many of them, but the key categories are PCA, or principal components analysis, and factor analysis. While principal components analysis tries to reduce the overall variance or work with the overall variance, factor analysis only works with shared variance. So PCA is very focused on taking all the data and represent with fewer components, while factor analysis is designed to identify common underlying themes. Because our goal typically is to only look at the first couple of factors or components, the results of PCA and factor analysis are very, very similar. So it wouldn't really matter in practice which one you would use, but indeed it is quite common to see academics using factor analysis more, while many practitioners using PCA more. Let's move into examining the requirements of the technique. One of them is that the sample size be large enough, that is, it should be 5 times the number of observations as number of variables. Both PCA and factor analysis work best when your data is either interval or ratio scaled. If the data is binary or categorical, there are other techniques that can be utilized, but not PCA or factor analysis. Some of the questions that one faces in conducting this technique is whether to use PCA or factor analysis, how many factors one expects to see, and what kind of rotation to use for the analysis. Here are the steps we're going to navigate through as we examine this technique. We'll first review the data to see if it's suitable for analysis or not. Next, we'll go on to identify the number of factors or components present in the data. Once we have identified the factors, we'll map the variables, the original variables, to the new factors or components. Next, we'll interpret the individual factors or components. And lastly, represent the factor or component for other analysis, like maybe as an input to regression. Let's begin by looking at an example data set to use for this to demonstrate the techniques. But before I even share the data with you, let me highlight something that we like to do when we're conducting PCA. Unlike supervised learning techniques, where there's one clear, unique solution that the algorithm will converge at, with PCA, we're going to get many good solutions. Figuring out which of these many good solutions is the right one is typically done based on some understanding of the data. This might come from previous existing theory, or it may come from knowing a bit about the relationships amongst the variables, or from literally reviewing what seems meaningful, semantically meaningful as one examines the variables. You may look at 3 or 4 variables and note there should be something common across those 3 or 4 variables, and thus expect them to coalesce into a factor or component. This is a kind of a priori expectation that's very important going into the analysis. This is not a hypothesis. It's more of an expectation of structure. Forming such an expectation helps you, helps you interpret the data more easily. Okay, so our example is going to be based off a tooth-based survey where people are asked about the benefits they seek from toothpaste. Respondents were given these 6 questions to respond to on a Likert type or Likert scale. Let's review each of these survey questions one at a time. As we do this, we're looking for any underlying themes in this data, some sort of common structure in the data, some way to put them together or bin them and group them. Let's review the questions one by one. It is important to get my annotations out. Okay, so let's. Okay. It is important to buy a toothpaste that prevents cavities. I like a toothpaste that gives shiny teeth. A toothpaste should strengthen your gums. I prefer a toothpaste that freshens breath. Prevention of tooth decay is not an important benefit offered by a toothpaste. The most important consideration in buying a toothpaste is attractive teeth. Each one of these items is discussing one of the benefits of brushing of toothpaste. The question is, are there some commonalities across them? Let's take the first two. It is important to buy a toothpaste that prevents cavities. It's talking about preventing cavities as a benefit. The next one is talking about shiny teeth as a benefit. The third one about strengthening your gums. The fourth one about freshening breath. Next one about prevention of tooth decay. The last one about attractive teeth. If you review this few number of times, you're probably going to start to see some common themes out here. You'll see that the first, third, and fifth are all aimed at some sort of health benefit from toothpaste. While you'll notice that the other three are focused on some sort of a cosmetic benefit. So you've got sort of health and a cosmetic or aesthetic benefit, like shiny teeth, breath, attractive teeth. This is a kind of a priori expectation that's very handy going into the data. You don't have to be an expert in the domain. Sometimes simply eyeballing the survey questions will give you some intuition about what to expect from your PCA. Okay, so going in then, here's what we're expecting at this stage. We're expecting to see two components emerge from our analysis, and these include a health component. Let me write that down here. A health component and a aesthetic component. We know that items 1, 3, and 5 are health components, and we expect items 2nd, 4th, and 6th to be aesthetic items. So we're expecting two components out here, and we have sort of a mapping of component to variable that we have in the back of our minds. So with this, let's go into conducting our analysis. So we have 30 observations, a pretty small sample. It barely meets the requirement, but it does. So it's 30 to 6 in terms of observations of variables. So a 5 to 1 ratio there. And all our variables are interval scaled. So the data is, at least at this point, we can say it's suitable for conducting a PCA. So let's go ahead and set this up in SPSS. What I'm going to do at this stage is I'm going to do all these steps you see out here, except, well, I will do almost all these steps. I'll get to these later. Right? So we'll do just the steps 1 through 4, skip 5, 6, 7, hit OK. Let's go to our data. Let me fire up the data, and then we'll run the analysis then in SPSS. The small little data set that I'm pulling up in SPSS, the file is called toothpastedata.sav. Here's the data. So you can see out here, we got there's an ID column. We got 6 V variables, which refer to the 6 survey items, the questionnaire items. We got a column called purchase, which indicates whether people's purchase likelihood. There's more about these variables in variable view. Let's take a look at these. So V1 V3 and V5 are about, again, cavities, strengthening gums, and tooth decay unimportant. And then V2, 4, 6 are about aesthetics. That's what we think a priori. Right? We're going to try and take these 6 items and shrink them into a fewer number of dimensions or components. The way we're going to go about doing this is to navigate through the menu, analyze, choose dimension reduction, and then factor. Now I want to kind of clarify this point here. Even though the menus in SPSS are indicating we're picking factor under dimension reduction, bear in mind this namesake grouping is kind of, this label is stuck for a while. SPSS has that in its menus. We're really conducting a PCA. The choice of whether we're doing a PCA or factor analysis will be made later. Even though we're selecting the factor option out here, we're not quite saying we're doing factor analysis yet. So to be more clear, let me make the screen bigger first. I'm going to make the screen a little bigger so things don't fall out of the screen. Okay, so here we are, dimension reduction factor. And now move the variables V1 to V6 onto the right, and then we'll select some descriptives. And then I won't do the extraction part just, actually, I'll click on extraction as well. Here, I just want to note something. I won't change anything out here, but I want to highlight a few things. One of them is that our method is default method principal components. So by default, we're conducting a PCA, not a factor analysis. If we wanted to conduct a factor analysis, we would select principal axis factoring. So we're doing PCA right now. A couple of other defaults to pay attention to out here are we're using correlation matrix. We'll always use this one. And we're also going to check a box for scree plot to get one more bit of output. We'll leave these defaults intact. We'll come back to these later if wanted. The only thing I'm going to do is check the scree plot checkbox here and move along to, that should be good enough, I think. At this point, I'm going to hit OK. We're not hitting rotation, scores, options. We'll save that for later. So our output looks as follows. We have some descriptives, correlation matrix, so on and so forth popping up. Let me quickly review what we see then. Our first bit of output is a bunch of descriptives on our 6 variables. As such, descriptives aren't very informative for PCA. For PCA, we are really interested in seeing the relationships amongst our variables, not so much about their averages and standard deviations. So the association amongst variables is assessed based on a correlation matrix. The correlation matrix here we get is really, really busy looking correlation matrix because it has a lot of redundant information. You'll see out here we have some variables here and some variables here. Well, all variables here. So 6 and 6. So you get a matrix of 36 elements, 6 times 6 by 6, or 36 elements. So we'll focus here on the top half of this table. And what this top half is telling us is that the correlation of prevents cavities and with itself is 1. Prevents cavities and shining teeth is minus 0.053. Prevents cavities and strengthens gums is 0.873, and so on. Let's focus on the big numbers in the column for prevents cavities. The big numbers are 0.873, well, of course, the 1, and minus 0.858. In other words, prevents cavities is correlated with itself, of course, and it's also highly correlated with strengthens gums, and also correlated with tooth decay unimportant, albeit negatively. If you recall, the 5th item was phrased in the opposite manner, so should be kind of, it's quite natural to expect then a negative correlation from that item. The key here is that for prevents cavities is correlated to other items that also talk about something about healthier gums and healthier teeth. If you look at the shiny teeth column now, you'll notice out there we have shiny teeth and prevents cavities. Correlation is negative. It's up like a minus 0.53. It's a nothing correlation. With strengthens gums is 0.155, nothing correlation again. But shiny teeth and freshens breath is 0.572. And shiny teeth and attractive teeth is again a big correlation of 0.64. The lower half of the table shows you the p-values for the respective correlations. You can see the ones that I've marked above are all significant, as noted in the p-values in the lower half of the table. Okay. So as you review this table, you'll notice the big correlations. They tell you a story. They're telling you a story that if you look along any of these columns, you'll see that you are getting correlations a bit like what we're expecting. Those who care a lot about the health of their teeth are going to score highly in all the health-related aspects of health-related benefits, while those who care a lot about cosmetic or aesthetic benefits will score high on all the aesthetic variables in our importance variables for toothpaste. Now, in terms of figuring out what does this mean for the analysis per se, it means a couple of things. In order to conduct a PCA, we want to make sure that our data is sticky enough, which basically means that we want to make sure, just like my analogy, that the sand will stick to some other cool sand particles, but not to everything. And the water molecules will stick to some other cool water molecules, right? There's some kind of stickiness in our data where variables are sticking to some variables, but not all variables. This is borne out by seeing some large correlations and some small correlations in the correlation matrix. So from that perspective, it seems like our data is suitable for conducting PCA. The second thing I'm going to look at here is to examine what is called the Barton's test of sphericity. So Barton's test of sphericity looks at the following. It looks to see if our matrix is different from an identity matrix. It conducts a statistical test of our matrix, comparing it to a matrix, a correlation matrix that is, where all the off-diagonal elements are 0 and all the diagonal elements are 1. If it sees a significant difference, then that would be indicative of a data that's suitable for conducting a PCA. A third consideration in seeing suitability for PCA is that our MSA is above 0.5. Indeed, our measure of sampling adequacy is above 0.5. So based on these three considerations, one can, confidently say that our data is suitable for PCA. Let's review the slide to, again, get a sense of what these three requirements are. So it's about suitability is assessed based on correlations, Barton's test, and measure of sampling adequacy. Now let's review each one of these one by one. The correlation matrix, this is what you saw in the Spss's output. Now, this is really busy looking, so it helps to be able to simplify, at least if your software allows you to do so, then do it. Otherwise, find some other way to simplify the picture. Here is one such picture. I've taken that same data and put that into a heat map. And we're going to walk through here, simplifying this picture. In this particular picture, the greens represent large correlations that are positive, the red large correlations that are negative, and the yellow or white represent 0 correlation. So let's go on here, and now to understand the process of simplifying the picture, let's think about how we can simplify what we're looking at. So in any correlation matrix, what's above the diagonal and below the diagonal are the, excuse me, wrong way. In this particular chart, the correlations, the ones are along this diagonal. So again, whatever diagonal has a ones, whatever is below and above are mirror images. So it's easy to then just say, I'm only going to look at 1/2 of the above. So the next slide is going to chop this into half, kind of like this. and also drop the ones on the diagonal, because correlation with oneself has got to be 1. So this heat map then kind of highlights for you exactly what we have concluded from looking at the output, which is that we're seeing sort of like, the cosmetic or aesthetic elements coalescing or having high correlations amongst each other, and the health aspects similarly correlated amongst each other. Our KMO's test indicated a measure of sampling adequacy was about 0.5, and Bartlett's test was significant. Now we can go into looking at the second issue. The second issue is figuring out in our data how many components are there. Now, it is extremely important before examining this step to have an a priori expectation of how many components one is going to expect. We're expecting 2 components, a health component and a aesthetic component. So important thing, we're expecting 2 components. With that in the back of our minds, we're going to jump in and examine our data to see how many components it really are. So there are a couple of ways of doing this in SPSS. One of them is the scree plot. Second is an eigenvalue we're looking for. The third is using total variance explained, and last one using extracted commonalities. Let's take a look at each one of these one by one in our output view. So in our output view, we have here our scree plot showing up. Okay. And we have a, we're going to look at next the eigenvalue more than 1 criterion, total variance explained, and commonalities one by one. Let me go through this in order. Let's begin with the scree plot. Our scree plot shows us, our scree plot shows us that as you go from that, the y-axis has eigens. So, component 1 has the most eigens then. Component 2 has fewer eigens. Component 3 has even fewer, 4 has even fewer, and so on. You might be interested in knowing what in the world these eigens, where they're coming from. Well, and I'm going to simplify this a little bit. Okay. So just imagine for a second that every component that you took your data and said, we're going to break it up into 6 components. Take all their data, roll it all up into a big ball, and then chop it up into 6 components. We'll give each component a 1 unit of something. That's something we'll give it 1 unit of is eigen. Okay. So initial, eigens are going to be 1. Everybody gets 1, sort of like here you go, component 1, you get 1, you get, so everybody is sort of like the same level playing field to begin with. And then we do that rotating the bottle thing, you shake all the data up. What happens is now, as you shake the bottle up, you turn the bottle rapidly, not shake it up, you spin it rapidly like a centrifuge. Your information gets moves around in such a way that things that are similar will stick together, things that are different will not. So what happens is now you had here a total of 6 eigens. You still have 6 eigens at the end of it after shaking it up because the bottle is sealed. However, the information has gotten redistributed. And you now have the lion's share of information or eigen in component 1. In fact, that amount is so large that it is 2.731 divided by 6 is equal to 45%, the number on here. And then you can look at component 2 is at 36.969%, and so on and so forth. Before I even look at component 2's percentage, let's focus on the actual number. Components 3, 4, 5, 6 all have eigens below 1. So one common criterion in figuring out how many components to go with is to keep all the components with eigens above 1. This is an SPSS default. The idea here is that if you all began with 1 component and you fell below the 1 component level, maybe you should be dropped then. So many people say, okay, here's the default criterion. Any component that fell below 2 eigens, we'll just axe them or sorry, one eigen will lacks them. So based on this rule, eigenvalue more than one criterion, we would recommend two components here. Now, let's now go back to our scree plot where we started out from. So these numbers, 2.731, come from the table above. Now, as you look at these eigens, for component 1, you have 2.731, then you got 2.218, and so on and so forth. You're beginning to see a very sharp drop off a cliff. High number here, and then a big drop. Now, some people like to think of this as a knee or an elbow. Whenever you're seeing this sharp drop of an edge is where you cut the plot. You say, okay, because there's a drop from the second eigen onwards, I'm going to keep everything above, right before the drop. So based on this rule again, or this heuristic, you would argue for keeping two components. So far, we've examined two criteria. One was the scree plot, the second was the eigenvalue. Let's move on to our third criterion. The third criterion is to ensure that we haven't lost too much information in conducting a PCA. We want to make sure that, think back to that puppy pic photograph, right? We had a picture of puppy, and we're concerned when we magnify, all the information deficiencies will be revealed. We're okay with losing some information, but not too much information. So again, that threshold is preferably 70%, but there are scenarios where you might say we're going to allow as low as 60%. So we want to make sure that this number here adds up to at least 60%, but preferably over 70%. The cumulative variance shows you the sum of 45.52 plus 36.969 as being 82.488% for the first two components. We want to make sure that number is at least above 60%, preferably above 70%. Based on that consideration, you could go with a 2-component, 3-component, 4-component, 5-component, or 6-component solution. I guess 6-component would be a trivial solution because it would simply mean we have as many components as variables. That was useless pretty much. So the choice is, do you want to go with 2, 3, 4, or 5? And so our goal is to reduce data. We would like to go with as few components as possible without violating that threshold of 60%, preferably 70%. Now, if you recall something about that pup, let's go back to that pup again. This is a good one, right? So let's go back to the pup again so I can highlight something about the pup picture. Here is, welcome back to the pup. Here's the puppy. Now, you'll recall when I zoomed into the puppy's eyes or puppy's nose, or puppy, let's use tongue now. The level of pixelation you're going to see is fairly uniform, right? Okay. So there you are. His tongue zoomed into. Now, the pixelation is uniform whether you look at the tongue, or the ears, the nose, whatever part of his body you look at, the pixelation is fairly uniform. This is where we see a difference between that analogy and PCA. You see, when you're doing PCA, there might be more loss from some components than others. So more loss in some variables than others. We want to make sure that no single variable is losing too much information. So imagine when you zoomed into the pup that the tongue was more pixelated than the ears, or the eyes are less pixelated than, I don't know, his neck, so on. If you thought that was the case, then, well, that would be more akin to PCA, where some variables might lose more information than others. let's see this, this information about extracted commonalities from the commonality table. So in the commonalities table, you can see we have all the variables have, full information in the beginning, but they end up with extraction commonalities of these, which basically means that while with two components, we're capturing overall 82.488%. We may still lose more information from some particular variables than others. You can see out here on prevents cavities, we're losing 1 minus 0.926. It's about 7.4% information. The next one, we're losing, again, 1 minus 0.723, which would be 27.7% information. So some variables like shiny teeth are losing more information than, let's say, prevents cavities as a variable. Now, we just want to make sure that we understand, we acknowledge that there will be differential information loss across these variables for dimension reduction, but so long as the information loss is not more than a certain threshold amount, like preferably 0.7, but definitely about 0.5, we're okay with some information loss, with information loss across our different variables. To sum up, we want to make sure every one of these numbers is above, every one of these numbers here is above 0.5, but preferably above 0.7. Okay. That was a lot, so let me just sum it all up in this slide. So our scree plot showed us we had two components because that's where the knee is of this plot. We saw in the total variance explained plot that if we can either go with keeping all the components with eigens above with 1, that would leave us with 2 components. We also saw that our total variance explained is a whopping 82.488%. That was well above the 70% and above the the lower bound 60% for that number. Furthermore, we looked at the extracted commonalities. We saw that every one of our variables has, they all began with starting commonality of 1, but all have extracted commonalities above the yellow line of 0.7, and definitely above the red line of 0.5. Okay, so at this point, you can say quite confidently, we are going to go with a 2-component solution. And the good thing is this does, align with our up-year expectation. We were expecting to see 2 components, and that is exactly what we're seeing right now. 2 components emerging from our analysis. The next step then is to map our variables to individual components. Now, in this stage, we examine each variable as a linear combination of our components. Let's see what this looks like in our data. We're going to go back to our output window, and here we'll notice in our component matrix, we have the following structure. In this structure, you'll note we have a component matrix. In this component matrix, we have components 1 and 2. And for component 1, let's start examining some thresholds here. Okay, so look at prevents cavities. Prevents cavities is really high in component 1, but low in component 2. Shiny teeth has a really high number in component 2, not component 1. Strengthens gums, high in component 1, low in component 2. Regression's breadth has a high number. That number, you're wondering what it is. It's a loading. These are called factor or component loadings. They're kind of like correlations. So Regression's breadth has a high loading on component 2. And interpreting them as correlations, you can see the number is, pretty close to 1. Tooth decay unimportant, high loading on component 1, not on component 2. And lastly, attractive teeth loading high in component 2, but not component 1. As you review these loadings, you probably start noticing a pattern emerging. Of course, we have two components, but within those components, you're going to see component one is about cavities, strengthening gums, and tooth decay unimportant. These are all, if you recall, about health aspects of or health benefits of toothpaste. While the other three, shiny teeth, freshens breath, and attractive teeth, loading in component two, are all about the aesthetic benefits of toothpaste. So we're seeing this dichotomy clearly out here, which thankfully is in sync with our a priori expectation. Now, that being said, what we are seeing is, yeah, indeed, prevents cavities got a big number for component one, but it's got a small number for component two. And I say but because it's not a zero. It's not, it's a pretty, it's not an insignificant number for component two. So what we're going to do in our next step is we're going to try and rotate the component axes to seek a clearer resolution of our components. The way we do this is by doing rotation, right? Exactly just that. We're going to rotate axes. So we'll go back here onto our menus, and we're going to pick an option that we hadn't done before. I had mentioned earlier that I haven't done rotation. Well, this time we'll do rotation. Now, under rotation, I'll click on here. The options are none is selected right now. I'm going to choose Varimax. The Varimax rotation is a way of rotating the component axes in such a manner that the two axes enclose a right angle between them. In other words, we rotate the component axes so that they are orthogonal. In the world of statistics, when two axes are orthogonal or at 90 degrees, you can think of them as being not correlated or having zero correlation between them. So Varimax rotation then is creating these synthetic components or creating components that are synthetically uncorrelated. This has value in certain contexts. So if we hit continue out here and hit OK, most of the following output will look very similar to what we had before. All the stuff here is going to be the same. The only difference you're going to see is in one additional matrix popping up. So we had a component matrix. Now we'll also see a rotated component matrix. This matrix is different from the previous one because we have rotated the axes. To get a sense of what this looks like, let's go on to our slides. So here I'm going to show you, visually speaking, what does it mean to rotate the axes? This is a visualization created in different software, but it does a very good job of kind of explaining, again, what has been accomplished by rotating axes. So if you think about our data, 1, 3, and 5 as being variables v1, v3, v5, where they're located. 2, 4, 6. They're kind of grouping nicely in this kind of this two-dimensional space. But you'll see out here that 1, 3, 5 are not hugging the axis, nor 2, 4, 6 hugging the axis, and 5 is kind of a little distant also. So what we do is we rotate the axis. Imagine you could move the axes, this axis here, and this axis a little bit like this. Let me get some curves in there, so it makes more sense then. So imagine you're turning the axes here like this in that direction. You have to hold the center, the origin constant, or you rotate the axes a little bit like this. What would happen then? Well, what would happen is if you rotate the axes, you'd get a picture like the one on the right. The 2, 4, 6 now are around the PC2 axis, and 1, 3, 5 are closer to the PC1 axis. What this does is it means that now the loadings of variables 2, 4, and 6 are all going to be high in PC2, but relatively low on PC1, more so than in the unrotated solution. Now, while we're at this, let's examine one more solution. This is Varimax. The constraint out here is that the axis should enclose a right angle between them. So rotate, let's say rotate TC2 one axis by 30 degrees. We got to rotate the other axis also by 30 degrees to make sure the angle enclosed is exactly the same of 90 degrees. Now, what if you remove that constraint? What if you said, okay, you can rotate in such a way that axis 1 and axis 2 can rotate different amounts. A more flexible structure then. Well, it turns out this is what is called an oblique rotation or direct complement option in SPSS. With this rotation, we find out that this angle here, even though it is pretty much 90 degrees, even now, we've allowed it to be less than 90 or more than 90, but it has turned out to be pretty much 90 degrees. In this example, it doesn't look much different, but in practice, you may find different sort of angles out here between the two components because it's free to do so. And because the angle is pretty much 90 degrees, the solution is not much different from that for Varimax. They look very, very similar in terms of solutions. Okay. So to sum up then, we have two rotation options available, and those are a Varimax rotation, which gives us this result, and the direct complement rotation, which we'll see in just a little bit. Let's drill down a bit into the Varimax rotation solution first. So here's the output you get from the rotation process. What we do here is we will okay, so we're going to interpret this result. Right, screen shared. Okay, so here is our rotated component matrix, and you can see out here, if we look carefully enough, that we have prevents cavities at 0.962, and on component 1, on component 2 is minus 0.027. Hopefully, if you recall from the previous result, this difference is much more striking than it was for the unrotated solution. Let's take a look at the previous one. So you can recall that, remember this 0.962 and minus 0.027. We'll go back to the previous component matrix, which was 0.928 and 0.253. So in other words, our rotated component matrix represents more clear difference across the two component loadings. In other words, we now have a more clear structure emerging, in that we see component 1 is more clearly having these three variables. Component 2 more clearly having these three. Let's take a look at what happens if you were to do a small reorganization of this result. So what I'm going to do is go back to dimension reduction factor. And all I'm going to do at this stage is go to options and make some changes out there to sort the coefficient display format by size and suppress small coefficients under, let's say 0.1, the default, or 0.15. So what this is going to do is, you'll see in the result, is modify our component matrix. So again, the first bits of output, all the same, all is the same. Even this is the same except for two things. The data has been sorted, so we have bunched together the high loadings for component 1 and the high loadings for component 2. The second thing we're seeing is that all the numbers below 0.15 have been removed. We're not seeing those here. Because again, they're so small. We want to basically see big ones and not see too many numbers in our output, so we can kind of hide numbers below 0.15 by doing what I did in the previous manual. Now that we looked at a Varimax rotation, let's take a look at a at a direct oblique rotation. So we'll go to dimension reduction factor. This time, I will make sure that our rotation is changed to from very max to direct oblique. And continue. Everything else is still the same. We'll go back to our output, take a look at the place where there's been some change. The component matrix is still the same as it was before. What is different is we do not have a rotated component matrix anymore. Now we have a pattern matrix. Whenever you do a direct oblique rotation, you get a pattern matrix, not a rotated component matrix. That's just the naming, the nomenclature that SPSS employs. So don't be thrown off by that difference in labeling of this table. That's communicating pretty much the same information as the previous one. So as before, we're seeing here quite clearly here, there's this nice grouping here of the two variables. We are drawing pretty much the same inference as we did in the previous rotated component matrix. That is, we've got a health component and a static component. Okay. So let's go back to that very max rotation then. And the reason I'm recommending going back to very max is, well, let me just back up a second here. It doesn't really matter, again, in terms of a result. It's pretty much the same whether we use a direct oblique rotation or very max rotation. But there is one benefit of very max rotation that I kind of like for what we're going to be doing next, which is the very max rotation constrains the angle between the components to be 90 degrees. Therefore, the two components would have zero correlation between them. This will come in handy in just a little bit. Before we do that, before we discuss how it's going to benefit us, let's go and actually run this. We'll go back to very max rotation and hit OK. Now, just note that our output is back to our rotated component matrix. Okay. Now, just for our own help, our own benefit, I'm going to go and edit this one out. Again, this does not affect our analysis in any way. It just affects our visual a little bit. So let me see. You gently in SPSS, keep persistently clicking on this one. You'll be able to get to this menu where you can, type in stuff like health. That's what it is really about. And so this way we know what these are. We're looking at our output table. Okay. So label these manually as health and aesthetic, just for our own benefit. It doesn't affect our final results in any way. It's just a cosmetic benefit to our output table. Okay. Now, what we're going to do next is we're going to see how we can interpret these. Specifically, we know we have a health component and a static component, but we want to extract these two components from our data. So what could you do? You could simply take the scores for prevents cavities, runs gum, and important, and combine these, average these, or you could combine them using you could pick a representative item, or you could use regression scores. Let me review that one more time. Imagine for one of the rows prevents cavities is some number like 3, strength gum is 4, 2 and more is like 5 or something. You could take these scores, you can combine them in some form, you could average them out. Of course, after reverse scoring to take important. The second option is, so that's a typical, so averaging is a very typical way that marketers typically take similar items and they average them into a construct. That's a pretty common practice. A second alternative would be, we could combine them, rather than combining it all, we could just pick a representative item. Say, prevents cavities represents a health construct. We'll just use this as our surrogate item. We could say, these are surrogate items. In all future analysis, these will represent the health and aesthetic components respectively, and that's that. We'll forget about the other 4 variables completely. A third approach we're going to use right now is combining them using regression scores. So we have here these loadings. These loadings can be thought of as weights, so that when we combine them, we could say, we're going to combine prevents cavities and decays to the unimportant. using these regression scores so that prevents cavity is going to get weighted a little more than strengthens gums, right? Because that loading is larger. And typically important will be have a minus because it is again a reverse score item. Let's see how we can combine them using these approaches. But before we do that, let me just review these concepts. So we're going to now represent our component either as an average score, weighted average, or pick a surrogate. So let's do this using we're going to go with the weighted average approach. Let's go on to Spss and run this out. So analyze, dimension reduction factor, and click on scores. We'll select save as variables here, and then click continue, or continue and OK. On doing so, we're going to get the same output we had before, so no worries about that. OK, and same output as before. The only difference is going to be in our data view. Let's go to our data view. Our data view looks as follows. We now have two more new components showing up. They call it FAC11 and FAC21. Again, don't ask me why they're called FAC and not comp, but it's SPSS view. Okay, so I'll click on variable view and I'll edit these out to make them more meaningful. I'll call these health, or just leave them the way. I'll just call it label health and health. The health factor, we know this is our aesthetic factor. So what we have here is a health factor and aesthetic factor from conducting this sort of from doing this. Okay, so now what we're going to do is we're going to examine so we've then derived a health component and aesthetic component from our data. Let's go in and see how we can utilize this for some downstream analysis. So imagine you wanted to now examine the effects of the linkage between these benefits and purchase likelihood. A company like Crest or Sensodyne might be interested in knowing, well, which of these variables have a bearing on purchase likelihood, which one is the strongest, biggest impact on likelihood of buying our toothpaste. So you have two options now. Either you can use the 6 variables or you can use the 2 components created. Let's go on. I'm going to actually use the 6 variables first so I can make a point about it. So if we were not using dimension reduction or PCA, here's how we would run a regression. It's a multiple regression, and I'm requesting our VIFs to examine the level of multifold linearity. Our output look as follows. Again, R squared 0.83, which is significant, and we move on to our coefficients. Our coefficients here, we're going to focus on. We see that some are significant, some are not. Let's go through the significance one by one. Prevents cavities is not significant. Shiny teeth is significant. Freshens breath is significant. Attractive teeth is significant. Clearly, the 3 aesthetic variables are showing up as being significant. But so you're quick to now say aesthetics matters, the health variables don't matter. Especially shiny teeth, freshens breath, attractive teeth are all predictive of purchase likelihood or important in purchase likelihood, but the other 3 are not. That's, it's a reasonable conclusion based on results. However, you must also pay attention to our VIF numbers. Notice 2 of them have crossed the threshold of 5. This means our inferences may no longer be reliable because our standard error is going to be inflated from having these huge VIFs for 2 of the 6 variables. Okay. So here's how dimension reduction will address this problem. So in addition to all the benefits that I've cited before about dimension reduction, the other benefit is if we were to use the components instead of the individual variables, we would get, I'm sorry, it's incorrect here. If we ran a regression as follows, I meant to do a regression, I ran a PCA a second ago, I don't know why, but anyway, back to our regression. If you ran a regression with health and aesthetic to predict purchase likelihood, we'll get the following results. So in review, our R squared 0.81, significant, and all that's good. Let's go on to the most important part of our output, which is we only have two components now, health and aesthetic. That's it. And let's look at the p-values here. You'll see health is not significant, aesthetic is significant. Most importantly, look at that. VI. If you've been watching VIFs for a while, you probably know that 1 is the smallest possible value for VIF. The reason it's so small is because, remember, health and aesthetic are components created from a varimax rotation, which constrains the angle between the components to be 90 degrees or forcing them to be uncorrelated. So VIF naturally is 1. What this analysis shows us is that with dimension reduction, we can come up with a very lucid interpretation for Crest toothpaste. You can tell them when you're advertising Crest or promoting it, don't highlight the health benefits because people don't care about that in deciding whether to buy the toothpaste or not. What they care about is our aesthetic benefits, so highlight them, talk about them. The aesthetic benefits could include talking about fresh breath, attractive teeth, and so on. Okay, so we've seen how we can conduct a PCA to then group your variables into components and then draw very, very nice, simple interpretations of your data based on the 2 or so components that are remaining. Okay. Right. So let me, before I move on to another example, what I'm going to do here is spend some time here examining other possibilities. So we have so far examined, well, what happens if you do this? You basically, if you run these 6 variables and go with all the settings we've gone with, what we get by way of result. Let's examine a few other possibilities. By that, I mean, in the past, I said, we'll go with the default eigenvalue more than 1. But what if your theory tells you there are not 2 components, but 3 components? You can specify that. You could say, I don't want to go with the eigenvalue more than 1. I'll set a factor of 3. Because my theory tells me I have 3 factors coming out of this. Okay. And if you do that, keeping everything else the same now, is it okay? Here's what we're going to get. The correlation matrix will be the same as before. These will be the same. What will change are the following aspects. Your total variance explained table now has not 2 rows that are going across, but 3 rows. Because we specified we want to see 3 components. So you're seeing also that the cumulative variance is this number here is 89% now because we're keeping 3 components. We're also going to see all the numbers in the extraction commonalities box have all gotten to be bigger than they were before because using 3 components. The squeak plot is still the same. However, what you're saying right now is we're going to cut the plot at this level, somewhere here. Oops. If I could draw a straight line, it would look nicer, but it's just the fact that it's so hard to draw a straight line because there's hardly a drop here. That's where we're saying we're cutting it. So clearly not a good solution, but the point here is you could, specify that you want 3 factors, 3 components, you'll get it. You can just tell the system, give me 3 components, and it'll give it to you. So you get 3 components here. After rotation, it looks like this. We'll try and see if this makes any sense. So here we get these 3 components. We can specify we have 3 layers of 3 components, and we get the 3 components. They look as follows. We've got this grouping of prevents cavities, duplicate importance, and then comes in one bucket. We got a second bucket here of shiny teeth, attractive teeth, and freshness breath is a third bucket. So we're getting these 3 groups sort of the items. It does make some sense though, to think about it. The first component is about health. Second is about aesthetics of teeth. The third one is about breath. It's a different kind of, I guess, maybe social concerns are more apparent out there. Okay. So you could specify the number of components manually, as I've just done here. And let me go back and undo that. We'll go to base and eigenvalue 1 and explore one more part we haven't examined so far. What if you wanted to do a factor analysis? Well, then you would go to principal axis factor. So when everything else is the same, hit OK, and here we go. So when we're doing a factor analysis, hence it says factor analysis up top. The descriptives, correlation matrix, KMO, MSE are going to be the same. What's going to vary are the following. So you see out here in our output, we have commonalities that don't have initial commonality 1 because a factor analysis works with shared variance, not the overall variance. So they don't all begin at 1. Since our goal generally is to focus on the first few factors or components, you'll notice your results here are the same. 2 components, 2 factors coming out of it. If you were to cut the sweep plot, cut right here, two factors again, right? So in all those considerations, 2 factors seems to be the best solution to go with. Instead of a component matrix, now we're going to get a factor matrix. We'll look at the rotated factor matrix. That's more meaningful to look at. And here we can see, again, our conclusions are pretty much the same. We again have a health component and a health factor and aesthetic factor. Okay, lastly, in going through all this experimentation I've been doing, I had the scores option box checked off, which means every time I ran this analysis, Spss has generated some more factor scores for me. So now I've got a lot of these FAC 1.2, 2.2, FAC 3.2, sorry, 1.2, 2.2, 3.2, and then 1.3, 2.3, and so on. So you kind of see these accumulating out here. So just kind of bear that in mind. Every time you run a factor analysis with the box checked off, you're going to get more columns being generated like this. So be aware of that first. So here's what's happened out here. And so when you're looking at your output, you want to be aware of what's going on here and pick the right sort of components for any regression type analysis you want to run with this data. Okay. All right. So what I'm going to do at this stage is I'm going to take a pause on this one. Actually, you know what? I'll wrap this up, and then we've looked at factor analysis already, and ran that. In many ways, factor analysis and PCA are similar in how it's run. There's a small difference in terms of who uses it and how the techniques work. In practice, the results are very similar. Right? So here's what we've examined so far. In this session, we examined motivation and dimension reduction, examined dimension reduction methods, conducted PCA, and finally conducted factor analysis. Just to kind of explain this issue, let me take a look at one more example before we wrap up. So the example I want to cover is the one of a different data set. This is a data set on a paper that I worked on a couple of years ago. We gathered data on a couple of measures of deal proneness of parents and children. Deal proneness, I'll share with you the scale. So you can take a look at the scale, and then we'll look at the data and run a PCA on that as well. So here is coming up here is the data. Sorry. The survey that we used for this study. And so you can see out here we have this is a survey done of deal proneness. Specifically, we asked folks to respond to 32 questions about their deal proneness or deal prone attitudes. Specifically, there were items about free gifts, a certain kind of deal proneness, deal prone behavior. Then we asked about buy one, get one free deals. So all these are about free gifts. And the next few are about buy one, get one deals, or 2-for-1 type deals. And then the next ones are about coupons. So you'll see all these items are about coupons. Redeeming coupons make you feel good. I enjoy clipping coupons out of newspapers, so on and so forth. And then the next set of questions were about cash rebates, manufacturers contests, and lastly about the sale. So we basically in this study we had 6 groups of items or 6 components, different components we're looking at. So naturally we expected to find 6 components from running a PCA. Here is the data, and so we had here I've prefixed the variables to make it convenient to identify them as FG1, FG2, and so on. So our a priori expectation is 6 components. 5 these, and 5 here, a couple more here, and so on. It is a reasonably, the data set is 116 observations, so, you know, not a large enough data set really for doing this analysis, but it may not pass the data size requirements. But this is hard data to get. We were not able to gather more data. So I'm going to go and run a PCA right now on this. We'll check a few boxes like we did before for descriptives and set this up for a PCA. We'll go with a fixed number of factors here of 6 because that's what we're expecting out here to get. As for sweep plot, rotation, we'll set to direct complement just because when you're gathering social field data from people, it is reasonable to expect there to be some relationship across the components. It's a less constrained model. We'll also look at varimax. I'll save the scores later on. For right now, I'm going to sort by size and suppress small coefficients below. Let's say 0.2 here. Here is the result we got. We'll get from running this analysis. So before I go any further, I just want to kind of highlight that the analysis we published in the paper was not of a PCA. We ran a factor analysis, and confirmatory factor analysis is a bit different from what you're seeing here we're doing in class. Okay, so here are descriptives of all the variables, not very informative. What we do care about is the correlation matrix. It's going to be a huge correlation matrix of 32 by 32. The key here is, as you look at these numbers, there's some big numbers, some small numbers indicating suitability for correlations for PCA. Our MSA is well above the 0.5 value at 0.85. Our Bartlett's test is significant, indicating on these 3 criterion, the data is suitable for PCA. We go on to our our total variance explained table. Here you'll see we have gone with 6 components. We specified that as a requirement. We put together 6 components variance. We get 72.866% variance explained by 6 components, which exceeds the 70% heuristic. In our scree plot, it's really hard to see what's a good point to cut it off. 1, 2, 3, 4, 5, 6. Here's where we decided to cut off, right? So here's where we decided to cut off the graph. This is always a tough question. Where should you cut based on the scree plot? And based on the scree plot, you should probably be cutting at maybe 2 or so. This might be a good place based on the scree plot, 2 or maybe even 4, maybe good one. But this didn't align so well with our theory, so we went with focusing on the theoretical aspect more. So we decided that 2 components would not make any sense or fit with our theory. So we've kind of emphasized our theoretical importance more. Okay. Also, if we had gone with just 2 components, we would have only had 45% variance explained. So we had a number of factors to consider out here. So 6 components seemed to make sense. It aligned with our theoretical expectation. The scree plot didn't look so good, but based on total variance explained, we met the requirements. We also met the requirements more or less for extraction commonalities also. So almost all of these are below 0.5. I know there are 1 or 2 exceptions to the rule here. There's one that failed to surpass the 0.5 requirement. Okay, and then we went on to look at, we can go on to look at the rotated component matrix. Here's the rotated pattern matrix, excuse me, or pattern matrix, which, because we ran indirect complement rotation as a pattern matrix. So there's a fairly good structure coming out here. All the free goods constructs items are aligning nicely in one bin, the first one. The contest one, another one, rebase in another one, and so on. So we're seeing sort of low cross loadings and high loadings for individual items. So overall, you would then look at this and say, these results are pretty close to what we expected theoretically, and we're kind of happy to see that sort of. Okay, so that was an example then of how you would run PCA by setting the number of the components you're expecting if your theory is very solid and you want to simply confirm your expectations. Okay, so to wrap up then, let me just go back to our final slide out here. We've gone over the motivation behind dimension reduction, explained dimension reduction methods, and conducted a PCA. We briefly looked at how you can conduct a factor analysis also using the principal axis factoring method in SPSS. Thank you.